Last class we talked about one-dimensional and two-dimensional collisions. One-dimensional collision is called head-on collision. In two-dimensional collision is called oblique collisions. So we have discussed all types of concepts, tricks and techniques of collisions between two bodies, between two particles. This class we need to do some more common examples in the form of conclusions. So I call it concluding examples. Let us take a simple example. Say a block connected to a spring, the surface is smooth, another body comes and hit the block elastically. Elastic collision and smooth surface. This is the assumption. Under these assumptions, find the velocities of the bodies just after collision it will pick up a speed towards left. In consequence, this spring will get compressed. We need to calculate the maximum compression of the spring. Maximum compression of the spring. So in this process, some momentum is delivered by the subject 1 to the object 2. If you want, you can calculate that momentum delivered during collision and the momentum delivered by the block 2 to the wall through the spring. So you can put this small questions and make it a passage or comprehension. Let us come to solve this problem. Basically, this is the collision of two objects. Object 1, object 2. If we assume the mass of this ball small m and mass of the block capital M, and velocity of the colliding object, let it be V naught. Now we have to choose a system. The system is two particle system. So what is the system here? The system is the block plus the bead. This is the system. During the collision, the time is very small. Since the time of impact is very small, the block will get displaced towards left very small. In other words, we can say that the deformation of the spring is also very, very small. How much the block will displace during the collision, that much the spring will be deformed. So deformation of the spring is very, very small. Therefore, the spring force is also extremely small. Because of the extremely small spring force, we can conserve the linear momentum of the system. Can be conserved. Initial momentum of the system is equal to mv naught minus I cap. And final momentum of the system, we need to calculate by assuming that this gets velocity v1, this, let us assume that the block will get a velocity v2. So final momentum of the system can be written mv2 minus I cap minus mv1 minus I cap. According to the conservation of linear momentum of the system of these two particles, the block and the bead, we can write mv2 plus mv1 is equal to mv naught, because we are equating final momentum with the initial momentum. Here, this is the initial momentum, this is the final momentum, and just removing minus I cap from both the sides, we are getting this. That is equation number 1. Next, Newton's empirical formula. Newton's empirical formula states that minus E into the velocity of approach equal to velocity of separation. Here approach velocity we can write minus A, since it is elastic collision. For elastic collision, E is equal to 1. So you just write 1 against the coefficient of restitution, and the approach velocity, suppose this is 1, this is 2, u1 minus u2, v naught or minus v naught, and the separation velocity minus v1 minus v2, u1 minus u2, and this is v1 minus v2. v1 is minus v1 I cap, minus v2 is minus v2 I cap, v1 is minus v naught I cap, and u2 is 0. In this way, you can write v naught is equal to v1 minus v2, or you can just write here minus and minus plus, your minus v1 minus 1 plus v2. In this way also you can write. You can check it again. Minus into minus, that is plus, minus v1 minus and minus is plus. So this is the second equation. If you solve these two equations, we can get the values of v1 and v2. Just rewrite these equations. v naught is equal to minus v1 plus v2. If you multiply with small m, both sides, this will get cancelled, and v2 m plus small m plus capital M equal to 2m v naught. So v2 equal to 2m v naught by m plus m. And if you substitute v2 here to get v1 equal to v2 minus v naught. and you are getting V2 equal to 2m V naught by small m plus capital M minus V naught. That's equal to, you take V naught common, so 2m minus m to small m minus capital M minus small m by capital M plus small m. So you are getting 2m minus m, the small m minus m. So this is the answer. Since small m is less than m, V1 can be written as small m minus m by small m plus m into V naught. Minus sign signifies that this ball will go towards the right because the left hand direction we have taken positive. So these are the velocities. These are the velocities we got. Velocities of the bodies just after the collision. This is the process I followed, the basic process. However, you can directly use the formula and you can get these answers. Now we need to calculate the maximum compression. The maximum compression. To find the maximum compression, we can draw a diagram. This will get a velocity V2 just after the collision. This will compress the spring to a maximum extent, let it be x. So change in kinetic energy plus change in potential energy equal to 0 because this is a conservative system. This is a conservative system. Only the spring force is there. Spring force is a conservative force. Therefore, you can conserve the mechanical energy of the system. Del K plus del U is 0. Kinetic energy loss is equal to minus half m V2 square. Potential energy of the spring changes from 0 to half kx square equal to 0. So x you are getting m by k square root into V2, and V2 you can just write the value of V2 from here, that is 2m V naught by m plus m. What the momentum delivered during the collision? Momentum delivered by this to this body is equal to change in momentum of this body or change in momentum of this body. They are equal and opposite. Momentum delivered the velocity of this body changes from m. Velocity of this body, capital M, changes from 0 to V2 and its velocity changes from V1, V0 to V1. So change in momentum of this body will be equal and opposite to the change in momentum of this body. These two bodies, they change their momentum in opposite direction because the net change of momentum of both the bodies will be equal to 0. That is what our conservation of linear momentum says. So momentum delivered is equal to change in momentum of the first body or change in momentum of the second body. Numerically they are equal. You can write that is m V2 or small m V1 minus V0. In this also you can write. Well, you got V2 is equal to 2m V0 by m plus m. So this is the change in momentum or momentum delivered during the collision. Next question, what is the momentum delivered by the block to the wall? The block is compressing the spring, and the spring, when it is compressed, it will push the wall. With what force? How much force the spring is exerting on the wall? The spring is pushing the wall in this way. The spring force. So the moment of this force, the spring force on the wall is equal to change in momentum of the block from this position to this position to this position maximum deformed position. So directly we can write the momentum delivered to the wall is equal to impulse of the spring force or that is equal to momentum of the block changes from mv2 to 0. So it is mv2 minus I cap, where v2 is equal to mv naught by m plus n. Let us take another example. Of perfectly elastic collision which is also known as plastic collision. You drop a stone, it will stick to the clay, or if you put a chewing gum or leave a chewing gum, it will come and stick to the floor of the room. It will never return, back, it will never bounce. Without bouncing back, this body, it will collide the surface with certain velocity v naught. When it is released from certain height h, v naught will be equal to square root of 2g into h. But it will bounce with zero velocity. This means that it will just stick to the floor. This sort of collision is called plastic or perfectly inelastic collision. E is equal to, if we assume that its velocity is v up, we can just write v by v naught. Since it doesn't bounce, v will be equal to 0. The relative velocity between this flow and this chewing gum is 0. Since v will be equal to 0, E will be equal to 0. Therefore, in plastic collision, the coefficient of restitution is always 0. So you can ask, in this plastic collision, how much momentum is delivered to the ground? In this plastic collision, what is the impulse of the reaction force or impact force acting on the bed or chewing gum during the collision? So this is a basic question. How much momentum is delivered? Momentum delivered by the bed is equal to change in its momentum. Because this is the earth, this is the bed. it's coming with velocity v naught. After the collision, its velocity will be equal to 0. When you consider the earth plus bead as a system enclosed by or given by the dotted line, collision takes place between these two bodies. One is the bead, second is the earth. Now question arises, can you conserve the linear momentum of the bead or not? Can you conserve the momentum of earth or not? Can you conserve the momentum of the system comprising the bead and earth or not? Well, so if you take the system as earth and the bead, this is a system of two particles. So when the bead collides the earth, question arises whether you will be able to conserve the momentum of the bead or of the earth or both as a system. That's very interesting and very intriguing question. Well, our common sense says that the bead was falling with some velocity, and after an elastic impact, the plastic impact, the bead will come to rest. Therefore, its momentum changes. Therefore, we cannot apply the conservation of momentum principle on the bead. Very simple. What about the earth? Earth was at rest and it will be at rest after the impact. Then you can say that we can also apply the conservation principle, conservation of momentum on earth. But this may be an incorrect answer in principle. Why? Let us see. As a whole, if you take as a system, they attract each other. While the ball is falling, the bead is falling. While the bead is interacting during the collision, the impulsive force comes into play. One impulsive force is acting on the bead, another impulsive force is acting on the earth. In this way, on this system, the net force is 0 if you take it as a closed system. Since net external force acting on the system is 0, you can conserve the momentum of the system. So how much momentum the bead is changing, that much of momentum the earth must be changing in reverse direction, opposite direction, so that the change in momentum of the ball or the bead plus the change in momentum of earth will be equal to 0. So how much momentum is delivered to the ground? The momentum delivered to the ground will be equal to change in momentum of the bead. And if I ask you what is the impulse of the reaction force or impact force acting on the bead, that's equal to change in momentum of the bead. That's equal to change in momentum of the bead. A third question you can apply, how much momentum change, how much momentum of earth change? If you say 0, is it 0? No, it's not 0. I explained why it's not 0. The earth seems to be static for all the times, but it's not actually 0. With respect to us, it may be 0, but with respect to space, the earth will go down or will be recoiled with certain velocity, but that velocity is incredibly small. I'll explain it. Is it 0? No. If it is not 0, then how much? Change in momentum of earth plus change in momentum of ball or bead will be equal to 0. Therefore, change in momentum of earth is equal to negative of change in momentum of the bed. What is change in momentum of the bed? Final momentum is 0. Initial momentum is minus mv naught j cap. So this will be minus minus plus and minus minus mv naught. Mv naught equal to square root of 2gh. So this is the answer. How much momentum of earth is changing? This is the change in momentum of earth, and plus of this is change in momentum of the bed. This is the change in momentum of the bed. That's what we can call the impulse of the impact force acting on the bed. That's equal to plus of this quantity. The change in momentum of earth is equal to minus of that quantity. How much momentum is delivered to ground is equal to negative of change in momentum or change in momentum of earth equal to negative of change in momentum of the bed, and change in momentum of the bed is equal to m into square root of 2gh plus j cap minus n will be there. So these are the answers. This is an interesting conceptual question, and after this I would like to twist this question in a different way. Well, let us take another example. This example is a basic example of a block connected to a spring and a bullet of mass small m. Block has mass capital M. The bullet is coming with velocity v naught, and you know that the bullet collides with the block inelastically, perfect inelastic collision equal to 0. It will stick to the block. It will stick to the block. During the process of collision, the deformation of the spring will be very small because the block will move, of course, towards left, but the movement is so small that we can ignore it. Therefore, we can conserve the linear momentum of the system. The system is the block plus bullet. Let me repeat. When the bullet collides the block, during the collision, the block will be shifted very little towards left. Therefore, the spring is compressed very little. The compressed spring will push the block with a very little force. F is equal to kx Hooke's law. Since x is very small, F also is extremely small. Therefore, this force can be disregarded. It is a non-impulsive force, and this is extremely small, can be neglected. When you neglect this external force on the system, we can conserve the linear momentum just before and after the impact. Just before the impact, the momentum is mv naught in negative x direction, and just after the collision or the impact, let the combined mass move with velocity v. Therefore, the momentum just after the impact will be equal to m plus m into v in negative I direction. So the common velocity will be equal to m v naught upon m plus m. So we need to calculate common velocity just after the collision. Next you can calculate energy loss during the collision. Energy loss during the collision can be found as the loss of energy in terms of heat, light, etc. is given by Q is equal to change in kinetic energy of the system. If you do from the basics, you calculate the final kinetic energy, you calculate the initial kinetic energy, take the difference, energy loss will be equal to this much. The final kinetic energy of the system, since bullet and the block both move with some velocity, the final kinetic energy can be given as m plus m into v square. Before collision, bullet was moving with velocity v naught, therefore its kinetic energy is equal to half m v naught square. And substitute the value of v here to get half m plus m, v equal to m v naught by m plus m square of this minus half m v naught square. And after one or two steps simplification, you can get mm by 2 by m plus m into v naught square. Next question you can impose, find the maximum compression of the spring. That is a relatively easier question. During the collision you can't conserve the energy because the process of collision is governed by the internal forces. Sometimes they may ask, what is the work done by the internal forces? During collision, this is the basic question. When the bullet penetrates the block, the bullet is getting a frictional force in opposite to its velocity. So on the bullet, the frictional force is directed towards right, and on the block, the frictional force is directed towards left. This frictional force is the impact force here, the reaction force here. The impulse of this force is equal and opposite to the impulse of this force. Since this frictional force is a kinetic force of friction because there is a relative motion between the block and the bullet, and you know that the total work done by a pair of kinetic force of friction existing in between the contacting surfaces is always negative. Therefore, the internal forces will do a negative work. And how much work? That is equal to the energy lost. So directly you can write that's equal to change in kinetic energy. Change in kinetic energy is always negative, minus half mm by m plus m into v naught square. The internal forces, that is the frictional forces, do the work, a negative work of this magnitude. Now we have to calculate this, let it be x. During the collision you can't conserve energy because the work done by the internal forces is not zero, and the internal forces are non-conservative forces. Therefore you can't conserve energy of the system during collision. However, after the collision, just after the collision, this block and the bullet will move with the common velocity and it will compress the spring. The spring will start pushing it towards right. Therefore, you cannot conserve the momentum of this system so long as it is in contact with the spring for a finite time. So, momentum conservation principle doesn't hold good. However, the energy conservation principle can be applied. The mechanical energy states that the conservation of mechanical energy states that change in potential energy plus change in kinetic energy will be equal to 0. When it will stop somewhere here it will stop. It will stop somewhere here, compressing the spring by a distance x, maximum distance x. So, the spring will get excess potential energy this much, the gain in potential energy of the spring is this much, and the loss of kinetic energy of the system will be equal to the final kinetic energy is 0. It will stop here instantaneously. Therefore, its kinetic energy finally is 0. The initial kinetic energy just after the collision is equal to half m plus m into v square is equal to 0. So, x is equal to, or half kx square is equal to half m plus m v. This v you can put here, m v naught by m plus m square of this. Half of getting cancelled. You are getting m square v naught square by m plus m. Therefore, the maximum compression of the spring we can calculate, m v naught by 1 upon k upon m plus m square root. So, in this way you can solve this problem perfectly. Inelastic collision of the bullet with the block connected with the spring, and here of course you cannot assume that the surface is rough for this procedure. So, you can assume here that friction is 0 between the block and ground. Now, question arises, if the friction is not 0, then what will happen? If the friction is not 0, what will happen? If we consider the friction between the block and ground, find maximum deformation or maximum compression of the spring. So, we can just extend. Here one subtle point is there. Question arises, when friction is not 0, during collision what will happen? During collision this will shift in this direction. So, frictional kinetic force of friction will come into play. Therefore, on the entire system m plus m, the net force is not equal to 0. We cannot say friction is 0, but the impulse of the friction, that is this friction into the time of collision, the impulse of friction is extremely small. Why? Because the time of collision is extremely small. Since the impulse of the external force is extremely small, you can conserve the linear momentum of the system just before and after the collision during the time of collision. Therefore, following the previous procedure, just after the impact or collision, the common velocity can be written as m v naught upon m plus m. They may ask you, what is the work done by friction? What is the work done by friction? Work done by friction is equal to mu m plus m into g. This is a normal reaction into x, but we do not know x. The change in kinetic energy is equal to minus half m plus m v naught square v square, where v equal to m v naught by m plus m. So this gives us minus m v naught square by m plus m by 2. This is change in kinetic energy. Well, and change in potential energy of gravity is not changing its potential energy because it's moving along the horizontal plane. So which potential energy is changing? The spring potential energy is changing. It's increasing from 0 to half kx square. Using these three parameters, we can apply the work energy theorem, which states that the net work done is equal to change in kinetic energy. The total work done between these 2 points or in this region or in this time before it comes to rest, instantaneously the net work done equal to work done by friction plus work done by normal reaction plus work done by gravity is equal to change in kinetic energy. Normal reaction doesn't perform any work because normal reaction is up and it is displacing in horizontal direction. The angle between the normal reaction and displacement is 90 degree. Therefore, the normal reaction does not perform any work. Work done by gravity is equal to 0 because gravity is acting vertically down and it is displacing towards left. The displacement and the gravitational force both are perpendicular. Therefore, the gravity does not perform any work. Another force is there, that is spring force. Work done by the spring is equal to minus half kx square, and that's equal to negative of change in potential energy. If you take it to this side also, it's okay. Or you can just write work done by the spring is equal to negative of change in potential energy with spring plus work done by the friction, that's equal to del k. And this is equal to minus half kx square. Work done by friction equal to minus mu m plus m into g into x, and del k is equal to minus m v naught square m square v naught square by m plus m by 2. So we can write kx square plus 2 mu m plus m gx is equal to or minus m square v naught square by 2 m plus m is equal to 0. This more interesting question. We are getting the quadratic equation and anybody can solve to find this quadratic equation to find the value of x. And rest of the problems we'll discuss in different pattern. Thanks all of you.